Hello Internet! Thank you everyone who watched, commented, or liked these videos. This channel reached 1,000 subscribers, and as a special thank you, I took a break from dissertation writing to make this highly requested video. False position method, also known as Regula Falsi, is yet another approach to finding roots of functions. Imagine if bisection method and secant method had a child. They would call it false position method. If you haven't seen my videos on bisection method and secant method, I would recommend watching them now. Don't worry, they're short. So how does false position method work? Given some function f of x, you use an interval a and b where f of a and f of b have different signs. That means that somewhere in between they must have crossed the x-axis. You compute the secant between those points, and where that secant crosses the x-axis you'll call up as point C. More on that later. Then you replace a or b with c, and keep repeating until you find the root. Recall that in bisection we always choose c to be the midpoint between a and b. Then we replace c with a or b depending on the interval. With false position method, we draw the secant between f of a and f of b, and where that intersects the x-axis, we call that c. We'll then replace c with either a or b depending on the signs. So how do we compute the x-intercept c? Using our example from earlier, we'll call the slope from a to b m1 and the slope from c to b m2. Knowing that slope is a change in y over the change in x, and we know that m1 is equal to m2, we can do the math and find this equation for c. Now that we have c, what do we do? If f of c is equal to 0, or less than some epsilon absolute value, then we're done. That's our root. But if not, we see if the sign of f of c matches the sign of f of a, and if it does, we replace c with a. Otherwise, we replace c with b. Then, we compute the next secant and repeat the process. Let's compare bisection versus false position method using x squared minus x minus 1 is equal to 0. And we'll try to find both roots, so we'll do this twice, one with the interval -2 to 0, and one with the interval 0 to 2. Here are our results for the first interval of -2 to 0. Bisection method is on the left, while false position method is on the right. And bisection took 24 iterations to complete, where false position needed only 18. And for our other interval, 0 to 2, bisection method still needed 24 iterations to find the root, but this time, false position method needed only 10. Notice anything odd about this data? The value for b never changed, and the values for a changed a lot at the beginning, but then slowed down afterwards. Both of these methods have a linear order, but bisection always has a fixed constant multiplier of a half, whereas false position has a multiplier of m that's dependent on the function that we're using. Some things to keep in mind: that false position method likes to stick to one point, as it did in our examples, and it can be just as slow as bisection, even though it's usually faster. There are ways to improve the performance of false position method, but in practice people will just switch to Newton's method or secant method once it looks like it's starting to converge. The code I used to generate this data is going to be hosted on GitHub. The link will be in the description below the video. As always, thank you for watching, and thank you to everyone who's subscribed to help reach this milestone of 1,000 subscribers. If there is a video topic that you would like for me to make, leave a description of it in the comments below, or if you just have questions about academia, grad school, or research, you can also leave those questions in the comments. And speaking of research, I should get back to writing.